Hello, everyone. Sorry for the slight delay. We had a small issue. So, welcome to today's webinar. It's our 37th webinar. Can you believe that? Um, I'm Pascal. I'm the ETP4HPC Communication Manager. I will be your host today, and my colleague Gabriella is also here to run the show.
Hello.
This a few practical information before I hand over to our first speaker. Um, the webinar is recorded, and you will receive the link to the recording tomorrow. This webinar is in listen-only mode, but you can ask questions. You can use the control panel that's illustrated here, the questions panel, to ask your questions. And you can also download handouts. So today we have the white papers that we are going to talk about. You can download them directly from the handouts in this webinar. And we have Manolis slides. Sorry, Robert, you did not send your slides, but I will add them later if possible. Yeah, concerning questions, we will answer all the questions at the end of the webinar, and we will put them in the chat so that you can all see them. Also, I would like to highlight that we're welcoming today again the participants from Castiel 2 and EuroCC in our webinar. They are supporting us for our webinars. So welcome and thank you for your support. So today's speakers. So we have two speakers today supported by our Sai. Robert Haas is the lead of hybrid cloud research at IBM Research. Manolis Marazakis is a principal staff research scientist at Force. And of course, Sai is here today. He's our SRA leader at ETP4HPC. He coordinated this huge effort, and his day job is a senior technologist and project manager at Partech. Sai, did you want to add anything about the SRA before we hand over to
Uh,
our speakers?
sure, yeah. So just a quick introduction is we are having this series of talks from the different work group leaders of the SRA 6. So there are a total of 12 research domains and 4 thematic trends corresponding to the different areas of HPC. And we address things like system architecture, storage and IO, those topics in the past. And today we are going to look at two very interesting topics: is non-conventional architectures and system software. And please note that after you hear the talk, please, I would very much encourage you all to go and read the papers which are now online for these two subjects and the SRA 6 master as well. So that's all, Pascal, from my side.
Thank you. So in the meantime, I think Robert was able to share his slides. Yes, we can see your slides. Thank you.
All right, shall I start?
Yes, you can start.
Thank you, Pascal, and thank you, Sai, and welcome everyone to this webinar on one of the white papers of the SRA 6. So this topic is now covered as part of the strategic research agenda for the second time. I was co-leading the activity together with Tobias Becker, and I see among the attendants now we have Alberto, Fabrizio, and Gianvito, who were also contributors and co-author to this white paper, and they will be here also to answer possibly some questions during the Q&A session at the end. Let me just show you briefly what I would like to cover. It's not essentially all the content of the white paper. Therefore, I welcome you to encourage you to go and take a look at the white paper itself after this session. But I wanted to give everyone a feeling of what we have described in this white paper, going from data flow architectures, going into what are today's essentially workhorses for AI and HPC applications, namely custom digital accelerators, and then looking beyond what is out there today and what may be actually very important for us in the future in terms of overcoming memory wall limitations using in-memory computing architectures, or going beyond that, looking at inspiration from our own brains and looking at neuromorphic computing, where I wanted to also describe some of the challenges, because there's a very active work in that space in Europe in particular, with workshops organized just in the last week or so that have raised again some of the same challenges that we have cited as part of this white paper. We cannot talk about all of this without looking also at data and the massive storage needs that the explosion of data is creating these days. So we will look at that as well briefly. And then I will wrap up with a few statements about the post-exascale vision and how all of these technologies will contribute to powering post-exascale HPC and AI installations, and more than those. I will summarize some of the key research and innovation recommendations that we made as part of the white paper, not going into detail for each of the single topics, but you will see that many of these recommendations are broad and they apply to all of these topics. And then some final thoughts and call for participations in a future version of this white paper. So let me just jump in right now. Data flow architectures, well, they are well known since at least the 70s, all right? And they take a different approach, alternative approach to traditional CPUs, when data is essentially brought to the operations and so that they can execute when data is ready. And these approaches have shown to be quite useful, especially nowadays in the AI space. And there are many implementations of those out there. I mean, some of them use systolic arrays, and you will see example of that in the paper as well. Now, with this kind of data flow architectures that are, as I said, alternatives to traditional CPU-based ones, there is additional effort that is needed in order to map applications through execution graphs into the hardware fabric. The hardware fabric can be hardwired or it can be reconfigurable. And it's a challenge for the compilers, and I'm sure Manolis will mention that as well later, to find the optimal mapping so that applications can really take advantage of these hardware resources and extract the most parallelism as possible. Now, for those looking at taking advantage of reprogrammable architectures such as FPGAs or coarse-grained reprogrammable architectures or CGRAs, there exist also these opportunities, and they've shown to be actually quite useful in scientific computing and probably also on the AI side. They've been, however, impacted by some of the difficulties of the low-level programming paradigms that existed. However, they exist already now, higher-level programming models for these data flow architectures that are available and that can help achieve this application specialization while remaining flexible. And you see on the right-hand side, a simple ways of explaining data flow architectures where data essentially is pulled out of memory and then flows through operation processing entities, data flow cores, as we say here. And as a result, the data flow cores don't have to go and access every time data from the memory. It flows through those cores until the results are essentially created and shipped back into memory. Now, some of these, the custom digital accelerator that we know today do take advantage of these data flow cores, CGRAs and other systolic arrays type of technologies. However, there is still substantial data movement needed between on-chip SRAM, scratch memory, off-chip DRAM, and the like. And this necessitates, therefore, energy and time. And if you plot, and you can see this from a publication a few years ago, looking at all the accelerators that were state-of-the-art back then, you notice that as you look at the peak power and the peak performance for these types of accelerators, there is a sort of this ceiling that one cannot really cross, and it is essentially caused by the necessity to move data back and forth and essentially the energy that is spent every time this has to be done, knowing that in AI cases, I mean, the model weights can be very big and you need to essentially move lots of data back and forth to process data for each single inference. Conclusion here is that if you want to go beyond that red line, achieving 100 or 1000 teraops with a total dissipated power of less than 10 watts, it's unlikely to go without some form of in-memory computing, essentially overcoming limitations of moving data back and forth and actually doing some spatial locality. Now, in that going now into that in more particular case, the in-memory computing, matrix vector multiplication core looks like what you can see here, essentially getting inputs and performing vector matrix multiplication and getting the outputs at the bottom of this block. This can be instantiated in different ways, and the white paper actually goes and covers many different approaches that exist out there. And I just flash a few here in terms of digital in-memory computing using SRAM memory. And there is a famous European startup called SRA AI that is going in this direction, as well as others such as D-Matrix. At the bottom left, you see an analog version of the same, which is done by a US startup called Encharge. Then there are analog in-memory computing using other types of memories, such as PCM and resistive RAM, where there exists also some startup activity there. And finally, also looking at flash memory, which is yet another company in the US. Now, all of these options have their own trade-offs in terms of facility to build these types of accelerator using existing technologies, or imposing additional constraints by bringing non-standard technologies into the flow of creating all this hardware. But they all can achieve different kind of performance points. One example we wanted to highlight as part of the white paper, because it's sponsored by the EU Horizon program, is from the NeuroSoc project. And here you see an example of network processing unit on this chart, which is composed of an array of smaller cores. A number of them are tagged AIMC for analog in-memory computing with embedded PCM memory in order to perform, as I showed before, this matrix vector multiplication very efficiently, together complemented by additional cores such as the green ones that are meant here to do local storage using SRAM, or the little orange ones that are digital processing units to perform the operations that cannot be efficiently done by the other cores. And finally, also a RISC-V that orchestrates operations across all of these different cores, and the use of the network fabric and the external interfaces and so on and so forth. So an example of a project that started probably now 2 years ago that is actually really going and demonstrating this capability specifically for edge type of AI applications. But again, those principles apply more broadly, and the architectures can also scale into data center type of use cases. Now, this was one thing in memory computing. I just wanted to highlight another aspect, which is now taking the inspiration from our own brains, emulating the sparse and asynchronous activity of our own neurons, and showing that we can excel at enabling this fast, energy-efficient decision-making and real-time processing of sensor data. You see on the right-hand side, on the top, a representation of our own neural networks and the spikes crossing our brains as our eyes are being excited by different types of images. This can actually be somewhat mimicked by an artificial neural network using spiking as the events that can happen in a sparse fashion, and therefore don't require the same energy and can actually operate faster than equivalent implementations that would be using typical artificial neural networks. The paper shows that there is actually a lot of activity in Europe in that space. However, there are still many challenges that will need to be overcome for this to actually make a breakthrough. I just wanted to highlight a few ones here, and they also came up, as I said at the introduction, as part of a workshop that took place just last week, if I recall well, hosted by Fraunhofer, called the STANCE Alliance. They came to a similar conclusion as we had already put in the white paper. Essentially, there is a need for enhanced compatibility between conventional software and neuromorphic hardware, having fair comprehensive benchmarks of the solutions, having standards and synergies in all this algorithmic and hardware development that is going on between different organizations, and last but not least, making wider availability and of this hardware for research and experimentation, which is obviously key to go and ignite a community around these efforts. Now, we talked a lot about computing. The white paper also touches a little bit about massive storage, and with all this explosion of data growth that we are witnessing from AI, but not only, we believe that there is a need to further innovate in terms of storage systems that can accommodate these, and also explore the use of AI in order to determine when to best exploit the different types of storage technologies that we may have available, and make sure that they can be integrated, such as these cold archive tiers, with the seamlessly with the standards that are out there, such as like object storage type of technologies. This section actually reflects very well with the white paper that is focusing on I/O and storage, which I also recommend for you to take a look. In our white paper, we spent a little bit more time to go and look at technologies that are legacy technologies that are going through a sort of a renaissance in this space because of their very interesting cost and efficiency density characteristics. And here I'm showing a graph that came from the INSIC consortium, predicting the growth of density of data storage on tape technology, magnetic tape technology. We can see here with the pink squares compared to the growth of density of storage on HDD technology that has been plateauing since now at least the last 10 years. So there are technologies out there that could potentially continue to grow and help us satisfy our needs for massive storage. There are others besides magnetic tape. Startups in Germany and in the UK are exploring other ways to store data also for the long term, in terms of having cold archival tiers. We believe that all these paths must be explored, but importantly, there must be a system level approach to this, how to integrate this and how to use AI to best manage this increasing level of complexity with different types of storage technologies available. Now I come to the post-exascale vision. As I just mentioned, there is increasing heterogeneity and specialization that we expect to continue growing, also in terms of hardware technologies. And that leads to challenges that I will know also well of architecting and exploiting this infrastructure with greater complexity. Now, besides the technological challenges, also come business challenges. And due to this increasing diversity, there's also a risk of spreading research and development investment too much across different approaches, or alternatively, focusing on just the more familiar ones at the expense of more disruptive ones. So these are aspects that one would have to take care of in making future decisions in terms of investments for future technologies. As I said, I didn't want to go through the detailed research and innovation recommendation that we came up with. You can find them in the white paper. I just highlight here the broader one that apply across the board to the different topics that we have covered, namely promoting larger scale deployments of these technologies and access to the community, possibly including open source hardware, fostering ecosystem of memory, accelerator, storage technology providers, companies, and academic and industry scientific users, developing programming models that can optimally exploit these capabilities, and simulating the development of unified and standardized programming models and software frameworks for enhanced interoperability. Final thoughts in terms of what we did or what we did not cover in the white paper. So there is more in the white paper that I didn't cover in this few minutes, essentially longer term work based on chemistry-based computing, including using DNA molecules to perform computing. This is work that is being explored and could really lead to significant breakthrough in terms of efficiency and performance. However, this requires still a lot of effort in the coming decade. There is other topics that are by design not covered in this white paper, that is a quantum computing, although it is a unconventional technology, but there is another white paper that is specifically looking at this. And now in terms of future topics that we did not cover in this version of the SRA unconventional architectures white paper, but that we plan to do possibly in the future, I've collected a few items here also from my colleagues in terms of future approaches for high bandwidth, low latency, and low power consumption in interconnect technologies, in internode, as well as across systems. DPU-like system, fully optical accelerators, photonics computing are all topics that are also interesting and that we could go and consider in future iterations here. I wanted to acknowledge the participation of multiple people. Some of them, as I said at the beginning, are on this call. Alberto Sconti from Links Foundation, Gianvito Ghese, Politecnico di Torino, Ken O'Brien from AMD, and Mattia Palladino from E4, as well as numbers of reviewers and content contributors that I've listed on this page. And with this, I stop and I will think and hand over to Manolis. Thank you for your attention.
Okay, thank you very much, Robert. So I will briefly share my screen for the, there was an error in the initial agenda. Sorry about this. So Manolis, are you ready?
Yes, I will need access
Yeah,
to
okay.
share. Yeah,
So I will give you access right away. So yeah, and while Manolis is getting ready, we had a question in the question tool. Are we going to share Robert's slides? Yes, we are. I will send them later. Okay, we can see. Yeah, perfect. We can see the slideshow.
excellent. So thank you for the opportunity to address the audience of today's session. You have heard about the ETP and the SRA and this set of white papers. I'm going to give you a quick outline of the one that is focused on system software and management, mostly in an HPC context, but you will see that the definition of HPC is becoming a bit broader. There is this concept of convergence between HPC analytics and AI workloads in a more unified computing environment. This has been a central theme of this particular part of the SRA, and it is now covered in this white paper. So I would encourage you to look up the SRA first and then take a look at the white papers. The white papers are of a more dynamic nature in the sense that we expect updates, and this will be to some extent driven by the feedback that we receive. So very brief summary of what we see as key elements of the current state. Well, from the point of view of system software mostly. There are the usual concerns about performance, but also efficiency, scalability, and there is this growing degree of heterogeneity in the hardware elements that we need to manage and make efficient use of using an increasingly more diverse set of applications. We see, particularly in the last couple of years since the last release of the SRA, that the role of AI workloads is more prominent. There are technologies that are coming up as important to consider. I will highlight the quantum aspect as well. It was a theme in the last SRA, but it's now again a theme, how to make use of it in the context of an HPC center. And also there are technologies that are less radical, but they are maturing still. I'm highlighting RISC-V, where there are several high-level initiatives within Europe actually to create competitive chips that would be able to handle HPC workloads. From the practical and hands-on point of view, which is really a very important part of this area of the SRA, we see the challenges of integration. There are quite important steps or levels of integration that have been achieved, but there is a lot of follow-up that we think needs to be done, and during my presentation I'll highlight particularly this aspect. There are automated build environments, but there are still not fully covering, at least to the extent that the authors of the particular white paper think, the requirements of more unified computing environments. So one aspect that we highlight in the white paper, and I would like to bring your attention to as well, is that we have a number of security challenges. Now, security not only in the sense of access control, but also in terms of auditability of the code and data that are being used for computing that might have a sensitive nature. And there are several dimensions to that aspect that I would like to bring to your attention and again get your feedback on. The convergence part, how to bring together infrastructure elements, data management, technical aspects for performance, but also security concerns about the execution environment has been a theme for us over successive versions of the SRA. We think that this convergence theme remains valid and also to some extent drives the requirements for the system software stack and also the management of increasingly more complex infrastructure elements that now need to support more diverse workloads, show more elasticity in how resources are allocated. And we do see aspects that have been more familiar in cloud environments, particularly multiple tenants on the same infrastructure that are becoming a concern, and therefore we need to plan how we handle such things. So these are interconnected requirements to some extent. Now, we have followed apart from the literature of internet protocols, and I'm just highlighting two relevant citations here. And this is called the hourglass model. And I'll show this in a pictorial way. There is this idea that you have applications on top, and then you have infrastructure elements on the bottom, and then you have relatively small set of key services that allow applications to make use of the infrastructure elements. So the hourglass model serves us to point where our work is focused, and I'm just highlighting on this graphic what is called the spanning layer. This is the terminology introduced in the literature for that part, and I'm just highlighting elements such as data management, resource management, and programming elements. Again, a topic that is covered in depth within the SRA 6 and in separate white papers. Now, this is what we are expected to achieve. Show a spanning layer, a set of key services that are well managed and kept up to date and offer the required functionality and features to the applications on top of increasingly more extensive resources and more heterogeneous resources. Highlighting again, we have CPUs and GPU arrays. We need to take advantage of high-speed interconnects. File systems are there, and they are very critical for hosting our data. Now, the harsh reality is that the waste on the hourglass model is not that thin, really. There are multiple domains and multiple vendors. So realistically, we are expected to support several software stacks. An easy example would be to say, well, I have my HPC oriented software stack, including an MPI implementation, computational libraries and such, but I have also my vendor-specific GPU libraries for accelerated computing on particular domains. And also for my AI requirements, I have yet more options for the software stack. So the picture becomes a bit more complex, and this is really the domain of effort by the people focused on system software and system management. So in the graphic, I'm just showing that you might have more diversity in the infrastructure layer at the bottom part. There are the multiple software stacks, either corresponding to domains or often to vendors. And then there are efforts for a standardization of key services. I'm highlighting POSIX standards for storage, MPI as a key element of the parallel programming environment, and also services such as PMIX that are focused on state information propagation, and this is an important part. Now, the high-level position that we express in this white paper is that we see increased urgency for flexibility in how we integrate software elements with such a multiple software stacks point of view. We remain concerned about efficiency, of course, But now we also are more concerned about workflows that are outside of the classic HPC being mainly long-running simulations of physical phenomena based on numerical computation, etc. So allow me to expand a bit on that part, again, with a kind of block diagram, and to highlight the key challenges that we try to discuss in our paper and offer a perspective about how to go about it. So it's software integration, efficient utilization of diverse resources, and enhanced security. This is done in the context of emerging technologies. As we said earlier, there are things like RISC-V that is maturing. There are technologies that show promise, such as processing in memory, but also more, I would say, emerging technologies around quantum devices. So we are expected to provide a system software stack following this model of the hourglass and the spanning layer. But now we need to have a new style of applications in the sense that a workflow might include elements of not only HPC simulations mainly, but also data analysis, and as well as machine learning workflows that perhaps assist the analysis of data or even try to accelerate the processing done as part of a multi-level simulation system in HPC. So what about the security parts and the data protection elements? Again, this is a core element of an operational environment, and I would like to highlight elements such as improvements in the security mechanisms at all levels of the system. There are data that might be sensitive and or even confidential, might include personally identifiable information. Again, there are strict regulations about handling such things, and these are becoming, I would say, more common cases in certain environments. And we are considering that one part of the solution there, and this is an element that I would like to expand on in the next couple of slides, that we need to have a verifiable software infrastructure. What I mean by that, we need to be concerned about what is the origin of the software that we are running, and make sure that it has not been tampered with, and we are really running what we think we are running. So part of the solution there is to have an automated infrastructure for building and validating the software components, and also combine them as parts of a software stack. There are the concerns about isolation between workloads and this trust establishment in the computation environment. And again, we think that one important part is that we need to have execution environments that can be verified, not just audited in an offline manner, but actually have more actionable indications about the origin of the software that is being executed. And then there is the concern that is quite important in the cloud environment, and we see this becoming quite important in latest generation HPC environments, that we need to be concerned about multi-tenancy. Several, not necessarily compatible users sharing the same infrastructure, not just having some sort of performance interference effect or resource competition effect, but being a bit more proactive on how to create a boundary between different tenants on the infrastructure. So I'll just expand on the topic of software factories, which is one of the new elements in this white paper. So the input would be, if you follow this metaphor of a factory, you need to have raw materials, and then you have products coming out of the production lines. So the input would be the various source code repositories, the build time configuration files, certain vendor-specific elements, including constraints in the order that components need to be built, plus some description, formal description of compliance rules and constraints. The core services are not particularly exotic. They are orchestrated build environments, dependency of platform to platform elements, checking of compatibility. So version 1 of one component, is it compatible with version 2 of another component? This type of logic. And of course, there is automation and test-based verification of what is actually achieved. So you need to drive this sort of core services, and you need to do that for performance checks, but also security checks, particularly the verification of origin, compliance to certain standards, which comes by following certain processes about how to build the environment. And overall, we can see this as an integration and interoperability focused task. So while several of these elements are there already, I'm just highlighting things like Easy Build Pack for packaging, for managing packages of software. There is GitLab to managing a variety of repositories and also processes on top of the repositories, Podman as an execution environment and automation environment. We see that there is a challenge towards creating a scalable infrastructure to handle this type of processes, and also to take care of the requirement for ongoing maintenance. This concept, we think, will become increasingly important, even critical for future HPC systems, again, from the viewpoint of having increasingly diverse workloads, not just classic HPC. And also there is the growing complexity of the execution platforms per se, with very different computational elements becoming available. In our vision, these are becoming available under a unified resource management environment, taking into account the presence of multiple vendors, and this is an element that really adds complexity to the services that are expected from a system software and management layer. So the software factory, again, we define it in the white paper as a tool-assisted or regimented process. So it's really a process, but it is heavily relying on tools. And the idea is that you have the capability now to build software with verifiable provenance, origin of each and every element that is being considered. So it's a bit more than a continuous integration and delivery pipeline, but it does bear a resemblance to that, and it covers the various concerns that we were talking about before. And the outputs that are produced from there are the executable versions of the various codes, including the system software itself, but also the computational libraries being used, the tools and stacks for the machine learning workloads, and technologies such as container images that are quite convenient for putting together a software execution unit, but also they need to be verified on their own. Now, it's a bit more complex than that because we need to consider multiple domains and multiple vendors. We don't see in the very short term a fully unified environment as shown here on the left-hand side of the screen. We see an environment where we will have at least such an instance of a factory process for the HPC part, because the software stack is quite particular, for the machine learning part, again, because there are particular aspects there, and for analytics in a cloud style, again, we expect to see a software factory pipeline taking certain special precautions to handle the requirements there. And again, integration as a very, very difficult challenge. Nobody loves it, everybody needs it, if you allow me this very blunt statement. For cross-stack testing and validation, we need to have a lot of infrastructure in place. So moving a bit further for that, again, we have dynamic execution models. This has been observed in prior versions of the SRA. Again, we have the various resources for computation, memory and storage, networking. We have containers, we have the cloud, and we need to orchestrate all these together. So a user of this infrastructure needs to achieve results. So we need to orchestrate the use of the hardware resources, offering allocation and scheduling services, taking into account balanced use of the infrastructure. We need to be concerned about fault tolerance. And again, we need to be monitoring this infrastructure at various levels of detail so that we have some capability to react to changes, be a bit more flexible or even elastic in the management of resources. These are topics that are covered in our white paper, just briefly listing them. Containers seem to be a very key technology for us, so we look forward to extensions and improvements in container technology. Portability is a concern for also assists reproducibility, but also efficient use of high-speed devices, including accelerators and network infrastructure is an area where we think that container technology needs to be improved. Again, virtualization as a method for more flexible abstractions for resources. Managing workflows where we need to orchestrate several tasks across diverse resources. This requires dynamic allocation and management of the available resources being used for computational purposes. And again, all this needs to be maintained in a way that allows us to take as much performance as feasible out of the actual infrastructure, which is quite expensive. And we anticipate, by the way, that the lifetime of such infrastructures will be slightly increased based on the complexity and high cost of acquiring such infrastructures at large scale installations. For the AI integration, I'm just pointing out that it seems there are requests for ready-to-use toolboxes. We interpret this as having pre-configured environments for development and deployment of the AI software stacks. And again, this has a direct impact on this concept of the software factory. We need to be sure what we are running, where our data are, and have some sort of auditing, but also verification capability. There are the expected demand for increased productivity tools. This is made a bit more urgent in the context of a workflow that includes AI elements. There is the classic theme of sharing resources, so questions of performance monitoring and provisions in the software stacks for efficient sharing. And particularly for model training, it seems that we need a different style of configuration, including aspects of the interconnect. And there is the challenge of integrating in existing HPC workflows. This would be the theme of HPC using AI for example, predicting certain computation aspects and then saving time in computing them from scratch. But there is also the aspect of running AI on top of the same hardware, basically, as HPC. So these are topics that are discussed in our white paper, and we expect to see in the coming short-term, mostly period, certain products coming out that might be along these lines. Post-exascale vision, again, a common theme, a common chapter across the white paper. So from the point of view of this particular white paper, and again, taking a point from things that influenced me personally. So in the last ISC conference of 2024, one of the keynotes highlighted in the citation there, it was reinventing HPC. Well, I'm taking a very limited view of what it means to reinvent, but one aspect is having AI as part of the workflows, and the other one is integrating technologies that usually were operated separately from the HPC environment. Again, highlighting the major challenges in the domain of integration and the emphasis on having more than one software stacks, all of them efficient on top of the same infrastructure. Again, this is an elaboration of the usual theme of convergence and efficient use of resources. I'm highlighting the value in having a process that gives you verifiable software artifacts. I'm also highlighting increased security requirements from the point of view of potential users of such infrastructure, not only for the code that is being executed, but also for the data sets that are being executed and manipulated there. So I think there is an architectural shift. It's not, we were not the first to observe that, that pushes us to consider very specialized modules for AI, for quantum computing, but also enhancing the performance and scale of classic simulations. If we consider this on a single platform or single infrastructure, actually, then this pushes the boundary for software elements that we are very much accustomed to, resource managers, particularly monitoring infrastructures, etc. And all these need to be revamped to handle the increased pressure for features. A very brief mention of energy and sustainability as concerns. There is a short mention of this topic in the SRA, and I would encourage you to pick this up. I'm just highlighting the aspect of monitoring. It needs to be in place, and it can be quite comprehensive and quite complex to get right. Ways to quantify the carbon footprint and then devise strategies, some of them online, some of them offline, for footprint management and reduction, actually. Okay. And there are the more classic concerns of, well, efficient utilization helps with energy and sustainability. Likewise, an element of power consumption and efficient utilization is to reduce the volume of data. So the prior talk provided certain insights across these lines. We see an increased need to improve in place and in transit processing, and likewise to take into account data allocation and expected transformations on substantial data sets under various constraints. So concluding remarks, I would encourage you to pick up our document and give us feedback. As I said, it is a dynamic environment. We would like to create perhaps a revision in the short term of that. We see this continuous adaptation to new technologies and requirements, no surprise there. System software remains essential. It will not be, we think it has to be a distinct layer in the overall or distinct element in the overall architecture of high performance systems. It cannot be, in our view, it is not beneficial to absorb it in each and every of the specialized software stacks. This requires continued investment because a lot of the software elements are quite old, and they need to extend. We need to extend them in directions that were not originally anticipated, and this has to be done at a fast pace. Okay. Again, main challenges around efficiency, but also integration, bringing together diverse technologies while providing reasonable performance guarantees. And then there is the balance question between performance and flexibility. The way that we have the white paper is that we emphasize the need for flexibility, but of course, performance is a primary driver for any design, and this is how such systems gain the acceptance of their users. With that, I'll conclude my presentation. Thank you all for your attention. Just showing acknowledgements from various sources for each of the main authors. And in the document, you will see also people that provided insightful reviews, particularly from the team of authors of the various white papers. So I very much appreciate their contributions. Thank you for your attention, and we will be happy to pick up questions during the panel session that is coming up.
Thank you, Manolis. Thank you, Robert. Thank you very much. So the documents Robert and Manolis were referring to are available in this webinar in the materials section. While Manolis was talking, I uploaded Robert's slides. So thank you, Robert. So you can now download both presentations in this webinar. So it's time for question. I will move to the next slide. Yeah, okay. So we already have some questions in the question panel, so I will get started. So first one is, well, not really a question. It's more like an offer for services, but I will read it out. So question from Deepak Katkoria. This roadmap is impressive. As AI demand continues to grow, HPC is likely to become a standard consumer PC within the next decades. During this transition, we can expect the emergence of new HPC architectures that are more edge-focused, application-specific, and power-efficient. Including SMEs in the development of cutting-edge HPC solutions for the upcoming AI challenges would be a significant win for the EU. As experts in FPGA and with a strong interest in edge-based HPC, logic dev believe there is a missed opportunity for us to contribute to this evolution. So I will take this one. So first of all, there are programs for to stimulate SME involvement, and if I can speak on behalf of ETP4HPC, we do welcome SME members. More than 40% of our members are SMEs. So many SMEs contribute to this SRA. We welcome members who have HPC research in Europe as full members, but we also welcome associated members which do not necessarily have HPC research in Europe. So contact office at etp4hpc.eu and we can tell you how you can become a member. So, question from Fabrizio Maguliani. Hi, Fabrizio. Question to Robert. What initiatives should Europe, both Euro HPC and HE, Horizon Europe, put in place? Sorry, I'm a bit slow this morning. So, what initiatives should Euro HPC and Horizon Europe put in place to achieve the leadership in the innovative, disruptive technologies mentioned in this white paper and in this presentation? Robert, big,
So
vast subject.
if I may offer some additional ideas here. Of course, there are the research and innovation recommendation that we have put in the white paper, and Fabrizio, of course, knows about that. But I mean, more generally speaking, I would think that it is an opportunity to jump on these disruptive technologies and try to gain leadership there versus try to gain leadership on the existing legacy technologies. I mean, that's a lost battle. I mean, I would rather go and focus on the new ones and disruptive ones and make significant investments there. And this goes along the same lines as what I said already. I mean, defragment the space, make significant investments, enable, establish environments for experimentation at scale for all the participants, the researchers, the users, and so on to go and try this out. And eventually also target products, right? I mean, it's good to go and try things out, but eventually we want this to become impactful for society here, and that's where these things could go and lead to. And I do believe that there are several disruptive technologies that we have highlighted in the white paper. And for several of them, I believe this is always an opportunity that one could go and take and say, let's go and make a big bet and push that. And in Europe, I think we have no reason to shy away. We have the smart people, the technology that we need to go and make this successful.
Thank you, Robert.
Just a very quick point is that one of the challenges we have had with these disruptive technologies is their lower TRL. So including that in R&I programs could sometimes be perceived as a challenge. But however, we have an opportunity, and we have been discussing this with our RIAG members, and hopefully it will be some of these elements could be included in the next MASP update, which is going to come up next year. And then hopefully I'm hoping that there might be pathways for getting some of these disruptive technology elements into future programs, at least from the Euro HPC perspective. So just a comment.
Thank you, Sai, for this precision. So let's go on to the next question from Henri Pierre Charles. That's for both Robert and Manolis. It seems that there is a bigger evolution on the hardware side and not so big in terms of programming language expressivity. For example, how to program in memory computing, how to express AI applications at tensor level, how to express data movements in data centers. Do you have the same impression?
If it's about
Manolis, you take this one.
unconventional, I was going to say Robert would be more than happy to say about the unconventional part. I can tell you my very conventional part that this is really where the pain is, I would say, particularly if you take the point of view of an operator that also needs to do capacity planning, etc. The peak scores reported are much lower than the usual performance scores reported. So part of the answer is that even people that are very performance conscious might not have the control knobs to touch the concerns that were highlighted in the question. So personally, I appreciate the question, and I think it will become a challenge. This type of expressivity, I think programming in memory brings it up a bit more visually as a problem. But even with more conventional technologies, there are limitations, and any effort towards improving description of where the data comes from, how it needs to be transformed before becoming usable, I think this is a very valuable direction to consider. But perhaps, Robert, you might have a more positive view than myself, or more optimistic, if I may say.
I would like to make a parallel, Manolis, to the AI world, where there is, tremendous innovation happening on a weekly basis, right? And I would say there is obviously very rich programming environments that are being developed, many of them in open source community fashions that are really trying to take advantage of all possible hardware optimizations that can be made available throughout, all the family of accelerators that exist today and will exist in the future. I just give you a few examples here, and this is also a question that came from Jean-Pierre Ponziera later. Yes, in-memory computing is a different beast. It's a different types of accelerator. It can offload matrix vector multiplication very, very efficiently. But yes, we integrate that into PyTorch environments, and this is like what is the norm today for AI developers, and that's how they can take advantage of these technologies seamlessly. For inference platforms, now you also have VLLM, which is a very, very popular one that is, really taking over the world in terms of open source. Lots of effort being put in there to be able to optimize how we run AI inferencing on different types of platform. You have OpenAI Triton, another open source activity that is trying to build kernels, particularly for AI, that are super efficient and can actually even beat some of the proprietary languages running on their own type of proprietary accelerators. So I would say if we look beyond the HPC scope and we look at what's happening out there, there is very active environment in terms of advancing at light speed, in terms of how we program and use all of these accelerators and do that always more efficiently. And we should take advantage of that as well here.
Okay, thank you. We are almost over, but we still have a lot of questions, so we will take them if we can. So question from Matteo Mascani from EuroHPC. Thanks for being here today. So question for Robert. Computing intensive data crunching move from CPU to accelerators as a general trend. The zetascale data sets are going to be highly heterogeneous, but of course potentially extremely large. In your opinion, how is important the direct interconnection, no syscall, between accelerator and data storage?
And it is out there already. And if you go and look in the AI space, you have GPU direct storage that is precisely implementing what Matteo is referring to here. So yes, it's important and it's happening.
Okay. Another question from Matteo for Manolis this time. Can the AI integration be considered as part of the hybrid heterogeneous Lippert-Eicher MSA approach, modular supercomputing architecture approach? Thank you very much.
I was going to say it is compatible. I would say the MSA is several years that has been put in practice actually. Several of the European, at least, supercomputers follow this template of a design. What we discussed in the white paper and with my co-author, etc., is more on the software side of things, which is not, I think, covered fully by the MSA template. and we are bringing forward certain requirements, including the proof of origin for the software sets and data sets that we think need to be considered. Now, the M.Sc I think is a very good template, practical template to take into account heterogeneous hardware in the form, for example, of dedicated partitions. So it has its place. We reference it in the white paper that we worked on, but we highlight elements that are more into properties such as provenance and other ways to follow the point of having multiple software stacks and being amenable to common management and control measures. I hope this gives a first level of response to the person posing the question.
Yeah, just a
Thank
very
you,
quick addition
Manolis.
is addition is that if I can encourage Matteo to have a look at the system architecture white paper. So there is some discussion on the modular supercomputing, and there you can see that there are some elements of AI that can be overlapped with the MSA architecture. So yeah, you'll find that's quite relevant.
Thank you. So we'll take a last question from Jean-Pierre Panzera, our chairman, so we have to take it. Regarding the disruptive technologies presented, neuromorphic in-memory computing, these are very promising from an efficiency point of view, consumption, performance, but still look difficult to program. So beyond dedicated appliances, when can we expect these technologies to be used for generic HPC or AI applications?
And Jean-Pierre, you're absolutely right. I mean, hardware without software brings nobody anywhere. So we need to make sure that there is proper enablement in the standard environments that users are going to be using. And as I referred to in my prior answer, yes, there are environments such as PyTorch that are being extended in order to take advantage of these new forms of accelerators, namely in-memory computing. So I believe we are actually on the path to make that more generally usable besides appliance for very dedicated applications only.
Thank you. And I think that with that, we are going to close today's webinar. I would like to thank Robert and Manolis for speaking today and for taking the questions. I think it was a very interesting discussion. Thank you, Sai, too, for being here. And we hope to talk to you again at our next webinar. It will be on the 28th of March, and it will be about OpenCube and Riser. So thank you to our audience, of course, I can't, and see you soon, I hope.
Thank
Okay.
you.
Thank you, everyone.
Thank you.
See you later. Bye.
Bye.
Take care.